Hello and welcome to PTI's educational webinar mini-series. Today we're going to talk about altitude, latitude, and shelf life. Certainly a very important topic as it relates to package integrity and the transportation of your packaging. So package integrity is really the package's ability to protect the product contents from environmental contaminants, three of which that are most important are oxygen, moisture, and bacteria. If they get into your container, it's certainly going to have an impact on most products that are reaching end consumers or patients. Now, the maximum allowable leakage limit is defined as the smallest leak that still is not going to impact the product over its shelf life. So every container leaks, but there is a certain leak size where it becomes critical for that product. So looking at distribution, understanding how your packaging reaches the end consumer or the patient is very important. So if it travels by land or air, it has a different impact. Air transportation is typically in a pressurized cabin, but that's still going to be at an altitude of approximately 14,000 feet. So it will experience pressures of around 650 millibars to 700 millibars. Whereas land transportation typically will be across flat land, but if it's traveling anywhere from the West Coast to the Midwest, you're certainly going to be traveling over the Rockies, most commonly the Eisenhower Pass or Eisenhower Tunnel. And that's at 11,500 feet. That will also expose your packaging to a certain lower pressure of around 650 to 750 millibars. So how that your packaging travels is very important to the shelf life of the product. And we'll go through that in a second. Also, this specific route, here you have a map of showing El Paso to Dallas. If that packaging is traveling from El Paso to Dallas, it's heading from west to east constantly. And the right side of that container truck will be exposed to the sun and will certainly heat up even more. Temperature has an effect on the packaging as well if there is a defect. So you just need to ask yourself, what is important to your package and what is it experiencing during the transportation? So Fick's law is a basic physics law that it describes what happens if there is a defect present in a package and how those environmental contaminants can transfer through that defect site and what's influencing that. So certainly if oxygen's on the outside of the container and you have a nitrogen-rich or nitrogen-flushed container, a defect will slowly allow oxygen through, but that rate of oxygen ingress will increase if there's a greater pressure outside the container than inside. So partial pressures will impact that. Temperature impacts that. As temperature increases, molecules, they actually float around at a higher rate. So temperature will affect the overall impact of environmental contaminants traveling through a defect. But the inert gas laws also play a role in that, and we'll talk about that in a second. The size of the defect and the length of that defect is a very big factor. So the larger the defect, more air can pass through that defect. So a 75 micron pinhole can actually allow air through that defect at 44 standard cc's per minute if the differential pressure is enough. If that defect is longer, so if it's a 20 millimeter channel defect, that ingress and that flow rate drops down dramatically. So it's just important to know that defect geometry definitely plays a role in how the product will last. Inert gas chemistry. This is the basic inert gas law, PV equals nRT, shows us the relationship between pressure, volume, and temperature. So as any of these factors changes, what happens to the container will also be impacted. And so the inert gas law and Fick's law, they work hand in hand. If the pressure outside the container goes up, it will drive environmental contaminants into the container. If temperature shifts, if the temperature inside the container increases or decreases, that will increase either the volume or the pressure inside that container. And if there is a defect, that means air will leak out of the container, and as pressure drops again, air will be pulled back in. So just remember, with that truck traveling from El Paso to Dallas, During the day, those containers might heat up dramatically. And in the evening, as it cools down, those containers might pull air back in through that defect. So during the day, those defects or the samples would actually exhaust nitrogen from a container, and in the evening draw oxygen back into the container. And it would do that cycle day after day after day. So how a container reacts when there is a change in pressure, volume, or temperature is really important to understand. So these three package formats all interact with those factors differently. So if you look at the large pillow pack, that will actually expand and contract freely as temperature or pressure increases. So it will expand and contract like a diaphragm, and it's far less likely to be impacted by just the cycling of pressures. So if there is a defect in there and you pull air out, you're actually going to be expanding the bag first before it's going to be pulling air out. And then as you repressurize the outside of a large pillow pack, it will compress over the contents before it starts drawing air back in through that defect. Now, the one thing that it differs from a stick pack is the pillow pack has a lot more volume in it, so it's also far less likely to be impacted by the same size leak. Whereas if you had a stick pack, it's a smaller volume, and a defect of 10 microns can certainly cause a rapid degradation of the product inside that stick pack. So a stick pack has smaller volume and is going to be have a shorter lifespan of performance given the same size of defect. Now relate that to the rigid can. A rigid can cannot expand or contract, so as the temperature increases or decreases, air has nowhere to go but through the defect, and a can will exchange oxygen and its contents and moisture through a defect much more readily. So as you have this flux of temperature and pressure, the can is the most susceptible to transferring of environmental contaminants through a defect. So the Eisenhower test, this is ASTM D6653. It's a slow drop in pressure, which is designing basically a truck driving up the mountain pass, and then it holds at lower pressure as the truck is driving over the mountain pass, and then again increases the pressure as the truck is driving down the other side of that mountain pass. And so this is supposed to simulate a transport of a package over through an altitude. It does take a while. It takes approximately an hour, if not more, but it tells you how the package will perform during that test cycle. Now, you can simulate that with a bubble leak test as well. The bubble leak test is known to be just looking for leaks, but you can stress the container in a bubble leak test operating at the right pressures to simulate that. But what you need to do, if you're doing a leak test with the bubble leak test, you actually have to expand the package fully to get bubbles to evacuate out through a defect. Whereas if you are just doing an altitude test, you just need to drop the pressure in that test chamber to the same pressure that your target altitude is set for. Now, ASTM D6653, it does have a table in that method that relates the elevation of a location and the typical pressure experienced at that elevation. So there's a good table in there that's very useful for reference. Well, the bubble leak test, though, it varies greatly in its performance. As a bag has more air or less air, it will either pick up a defect more readily or less readily. So that's something very important to understand. The performance of the water bath leak test is highly variable. Now, the performance of the water bath also varies as a package has more or less volume in it. So a larger package has more volume, will expand more easily in the water bath leak test, and therefore the larger package formats, a larger defect was more capable of, or a defect is more capable of being detected with those large package formats. As the package format becomes smaller, such as a stick pack or a sachet, the package has more surface area and is more likely to expand in that water bath test and is less likely to create a driving force. You're just not going to find bubbles as easily. Whereas vacuum decay can pick up those defects very easily. So another issue with the water bath leak test, if you're using it as an actual leak test, it's a costly leak test. So depending on the product and the weight of it and your uptime and how often you're testing that product, a typical production line that's using the water bath leak test is creating a destructive it's a destructive method, and you're throwing out approximately $300,000 worth of product per year, depending on what that product is. So the idea here is the water bath leak test, you can simulate some things, but it can also be costly. So an alternative to that is a vacuum decay test method. In vacuum decay, very simply put, we're pulling vacuum on the container in an enclosed test chamber. So we're drawing vacuum down and monitoring that vacuum level. And if there is a good leak, that means that the air will, or if there's a good container and there is no leak, the air pressure will be stable in that test chamber. Whereas if there's a defect, air will leak out and you will see that pressure increase. Now also, you note that we are going down to 500 millibars for this vacuum leak test. We can actually operate the vacuum decay leak test at any pressure below 800 millibars. And in that way, we're able to actually produce a simulated altitude for the duration of that test cycle. So remember, ASTM D6653 is testing the altitude over an hour. We can challenge the package's integrity over a short 20-second, 30-second, or 1-minute test cycle to get a very sensitive leak test. And that 1 minute will also stress the container to see if in fact there is a risk that the container will burst at that pressure. You can also operate that leak test at 500 millibars or a more aggressive pressure to really make sure that you're not going to have a weak seal for the product's transportation. And vacuum decay is an ASTM test method, F2338. It's a sensitive test method. There's a variety of ways that you can arrange containers for the test method. You can see in this image on the right how multiple containers can be tested at one time. And so you can do rapid testing and really crank through a lot of product while also achieving very sensitive leak test results down to 10, 20 microns. And that is also stressing the container such that if there is an altitude risk, it would be detected in this leak test. So with that, I thank you for joining us today to discuss altitude, latitude, and the product shelf life. Thank you for joining us, and look for many more webinars.